Okay, I won't follow the clock at the far end. I shall follow my watch, and if I go beyond half an hour, throw me off. I've been rambling excessively. Okay, with a slight apologies for the hyperbole of the title, but this in part is stimulated by the fact that we as a scientific community, or scientific communities, just about never publish our problems. I'm funded through NERC, and in NERC, a neutral is a negative, a positive is a neutral, and a superlative is a slightly positive. So even look at their grading of grants, with alpha 1, 2, 3, 4, 5, and so on. And therefore, we are not, by and large, willing to admit our failures, but I will lay a very significant failure in front of this audience today. Most of you probably know, but just for background for a few, we've got a few slides to lead into what is CCAP, the Cultural Collection of Algae and Protozoa. So what are we? CCAP is, in modern terminology, a biological resource centre. It holds a uniquely diverse range of protista taxa, the only other microbial collection in the world with a comparable biodiversity from a phylogenetic perspective is the ATCC in America, which is debatably broader than CCAP. CCAP has a sub-collection of achlorophyllous protists. We now know that being an alga is not being a monophyletic group. Algae is a way of life, if you like. They're just photoautotrophic organisms, whereas many of the algae are phylogenetically intertwined with their achlorophyllous protozoan relatives. This is a tree by Sandy Balhoff from, I think, about 12 years ago or now, and the things rounded, the circles around them are where CCAP holds exemplar taxa, so you can see really quite a diverse range of things. This is a slightly more modern tree, and I like it because it has a stem, and also allows me to circle the cyanobacteria that the collection holds. We provide our living material and support provision. This is funded by the NARC as part of national capability funding, so we are like a ship or an Antarctic station from a perspective of their taxonomy. And the sectors that we service from CCAP include the ecotoxicology and biocide testing, very applied activities, aquaculture, HAB, harmful algal blooms, which are a big deal in the context of the Scottish economy, because aquaculture, mussel aquaculture is a very big industry in the west coast of Scotland. And we're obviously providing materials for teaching, the traditional market, if you like, of blue skies research in the academic sector particularly, and applied R&D. So the latter 2 points, I would say, in my career involved with CCAP over the last in excess of 20 years now, is where the barriers have become very, very blurred. What is now an academic exercise and what is a commercial exercise? And this is a direction of travel which I suspect will continue for the foreseeable future, where scientific research in institutes and universities becomes increasingly applied or on the edge of applied research. Having a microorganism or having any biological resource, whether it's a monkey or a virus for that matter, without knowing anything about it, has limited value. Yes, you can go and see the monkey in the zoo and say, that's interesting, that's a monkey. But if you know a lot more about it, or the virus or the bacteria or the algae, then it has increased value. What I like to think of our organisms is that they are de facto biological standards. So you have a standard material in which you can build your science story on. And science is sadly largely sequential rather than eureka. I'm still waiting after now 30 years to have a eureka. Any day now it's coming. But what is key is what is written, what is understood, the genetic material, the codes, the whatever, the metabolomic data associated with that biological resource. And this again is a direction of travel for biological resource centres worldwide, whether it be Kew Gardens, a zoo, or a microbial collection such as ourselves, is that the data associated with the organism is key. quick anecdotal example of this is if you do ecotoxicity testing on 2 little green blobs. If you don't know what that green blob is, you can have up to 10 to the 3, potentially even 10 to the 4 in the concentration of different susceptibilities of 2 different algae to an individual toxicant. Now, if you're trying to compare one with the other, this is clearly a completely flawed thing to do. So if you don't use, this is where I would rattle on ad nauseum about the importance of strain numbers, of having a non-changeable marker for whatever your biological resource is. Don't forget, taxonomy is extremely fluid. You get 3 taxonomists in a room, you're going to get 4 definitions of what that material really is. One of them will not have made up his mind. The other 2 will be so adamantly concerned that it is a monkey or it is a banana, and they will not change from that. So the one in the middle nearly always wins, but they can't decide. So non-changeable numbers are key, and they now with computer technology we can link things so much better than we could effectively a generation ago. I thought to highlight training beyond what we have historically done. Yes, we involved research students increasingly in collections such as mine. We have CPD provision for in our case, the growing aquaculture and biotech sectors. Based on the sort of work that we did in CCAP, we've built a master's in algobiotechnology that is delivered by University of Highlands and Islands and Aberdeen University. UHI does not have a research degree awarding powers yet. And at present, I personally have students at Cambridge, Bournemouth, Edinburgh, University of Sao Paulo. So you're starting to see more of a global connectivity in biological resource centres as well. And my collection is by no means unique. Outreach and engagement, my goodness, we do strange things nowadays compared to 20, 30 years ago. The strange things on the top is the Institute of Architecture here in London, where an Italian architect wanted to symbolize regeneration and sustainable development in building, and so they had these strange installations. And it's quite fun. The traditional stuff with kids, and of course our scientific collaborators and associates. That chap there with me, standing behind me, was then Secretary of State for Scotland. He's no longer in that role, but being based on the west coast of Scotland, you have a continual flow through, because there aren't that many high-tech organisations on the west coast. You have a continual flow through of politicians and the like. Anyway, back to the biological resources. The challenge, there's a significant challenge. Is your material fit for purpose? Do we really understand it? Is it just, that's okay? Is it unchanging or unchangeable in the way that we maintain it? And we actually have very little evidence one way or the other for most biological resources that are held in collections. One example of where we do have some data is for this organism Chlorella vulgaris, which is an ecotoxicity testing strain, which was isolated 130 years ago almost now, and we know from studies that we did that genetically this material may not have changed. We don't know, we can't get in our time machine, but it was held separately for about 45 years in different collections, and we checked it, and it was genetically, as far as we could tell, identical, certainly functionally identical. So there are examples of organisms that were maintained by serial transfer for huge lengths of time that have not changed or not changed significantly. As I said, the traditional method of maintaining our cultures is quite unusual in the context of biological resource centre, because we are still using serial transfer as the method of choice for the vast majority, well, not the vast majority, the majority of our holding. Some 35 to 37% of CCAP is cryopreserved, and the rest is all maintained by serial transfer. But is this an appropriate methodology? Well, we don't know. It's largely the only method that we have available, and I pulled this together largely from my own personal experience, but also in part from what I can find in the literature. There's a much better literature on failures in pathogenic protozoa. they seem to be less frightened of telling you about how useless they are, where the rest of us, perhaps because we're so frightened of not getting funding, we will not admit that something has changed. But the scariest of all of these is the one at the top, because this was a contemporary of mine, a PhD student in Dundee back in the 1980s, and he started working on alkaloid neurotoxin production by Anabaena flossacea, a cyanobacterium, and it lost this attribute. Certainly more recently, we've been working quite a lot with the aquaculture sector on Pseudonychia, a diatom, which is a major issue in aquaculture. It produces a very potent toxin, again, and it loses its toxin producing domoic acid production capacity as well. It also shrinks irreversibly and disappears in culture after a while. Again, to this audience, there's no point in going in detail here, but these are the sort of methods which either depend on slowing down growth or removing water that are available for holding microorganisms per se. But in the case of algae, it's only cryopreservation that is an appropriate long-term method. Although you can store resting cysts, for example, of planospores and aconites, resting stages of both algae and cyanobacteria in a dried state for very long periods of time. But there's, to my knowledge, no real significant shelf life studies being carried out on these organisms. So, standard practice, back to what John was doing back in the early 70s. The method really here hasn't changed significantly. Two-step cryopreservation, controlled rate cooling of some sort, and plunging. And in the case of CCAP, we are holding the materials largely in liquid phase, liquid nitrogen. And this is down to the unsophisticated storage vessels that we used and have used historically. This is what we have been satisfied with. Again, for this audience, there's little point in reiterating the lists of problems and issues that are associated with slow cooling, but we all know there are lots of stresses involved, and these stresses have implications to viability levels, the amount of damage our material suffers from, and our capacity to recover those materials. And sadly, nobody, not least myself, has got round to revisiting this for the last 10 years, but these data are from work that I did with the UTEX collection, where we looked at what we'd tried to do over the preceding 15 years probably, organisationally, and looked from a taxonomic perspective of what we'd tried to do and what had been successful. The group here that I'd like to flag up, not least because I'm going to talk about miserable failures later, are the Euglenophyta, where we apparently have quite high levels of success, but we have found real issues with repeating that, and have not had anything like in recent years that 70% success. That 70% is probably flawed data on the basis of lifting data from card indices, old card indices. I just wanted to put this in as an issue, and again, this is data I've stolen from Brian and John about the issues of storing in liquid nitrogen. We talk about the damage that can cause our organisms through the cooling process, etc., and potential issues on storage. But by and large, certainly historically, CCAP is not worried about the materials themselves. We've just said that's fine. But storing in liquid phase, liquid nitrogen, I don't have exact data in my head, but I would say approximately 10 to 20% of the vials leak. And we're getting something between 10 and 20% of the vials when we take them out and thaw them. They're hissing in a slightly frightening, violent way. And of those 10 to 20%, I would say almost all of them, if they were azenic before, are not azenic afterwards. And for that matter, even though we try to be very cautious and very careful, decontaminating the vials before we open them, we're getting a minimum of a 10% contamination rate on vials that have not leaked liquid nitrogen. So there's a significant issue there for holding azenic materials in our storage vessels, at least. I'm not quite sure why I put this slide in, other than to show that in theory, in an ideal world, this is what one would do in a biological resource centre culture collection, where you would get your original material and you would have a master bank, and then you would have working bank, and you would have lots of quality control testing of efficacy of your storage method, and of course of the resource, whether it was functional or genetically identical before and after. The reality is that one doesn't have the resources to do this in a collection such as CCAP, and I suspect any other biological resource centre anywhere in the world. But where it works, it works. At least that's what we would like to think. And I know that there's ongoing discussion about an overarching longevity manuscript, which I've certainly heard of from John, and I've heard from Roland and from a number of other people, but it doesn't ever seem to shiggle on any further. But this is work that we published way back in the 1990s, where we took some of the original materials that John had cryopreserved, where we had good data and sufficient replicate cryovials in storage, and for periods of up to 20 years plus, we found no statistical difference in reduction in viability, and that was extremely exciting and extremely positive, and a very good sales pitch for trying to ask for extra resource to cryopreserve our materials. So that was extremely positive. In that same paper, we looked at the storage regime, and this storage regime will be probably again familiar to John, but nobody else would do this today. We had basically wide-necked dewars that were like rubbish bins, and we manually lifted a transfer dewar which looked like a turnip, so these things were called bins and turnips, and we poured the turnip into the bin. And we did this twice a week, and we did this forever and a day. I wanted to look at what was happening during that process, so we put temperature probes in different places in a stack inventory, and basically there was effectively no difference in the storage. What the black triangles are, and I had to remind myself of this, are where we physically poured nitrogen in and filled, and really there was no significant difference. The red triangle is where we took out a sample from a stack beside the stack where the probes were. So again, that had no effect. It had an effect on the stack that was being removed, but it didn't have an effect on the other stacks in the store. And we also replicated removal and addition of cryovials. And yeah, we had one little spike that went over -120, but by and large, there were no significant thermal issues of manipulating using the method that we used in this paper, at least. Although I have visited major collections, which remain nameless, where I've seen them take an inventory out and leave it literally for a minute plus on the side while they in Northern Irish footered around, and I felt really, really stressed. I felt like jumping in and physically putting it back in. And if they've done that repeatedly, I suspect that that's had an effect on the viability of their samples, potentially. I know anecdotally from the Cabby collection, which is not where I saw this happen, that they used to have wide neck dewars, and they didn't have good data, but they had an empirical feeling that the material stored at the top was not as robust as the stuff stored at the bottom. Unfortunately, they didn't have data to substantiate that. But clearly we're all familiar that if you take a sample out, it warms up very rapidly, and this could have issues to the cryocrisis. Okay, this is where I say I went away. I delegated to the person who normally did the filling of the dewars. They omitted to do so. The person who should have been the check in my absence, I normally would check that they had done it. The person I delegated to check that they had done it didn't check. And the upshot was that I arrived back on a Monday morning, checked the list in the lab where the things should have been ticked off. It hadn't been ticked off. I thought to murder somebody, but decided that was inappropriate, paperwork too much. Rushed down to the inventory and saw that it appeared to be boiled dry. I don't know whether it was, whether it wasn't, but I didn't spend any time checking. I put the hose in and I switched on and I filled the inventory, and then panicked. What we did after that is that we took out a range of organisms from different parts of the inventory, and you can't see because I've on purpose made this much too small for anybody to see. But just look at the greens and the reds. That's what's important. And we did a basic viability assessment, i.e. recovery or no recovery, on exemplar vials from throughout the inventory system. And we looked at how that compared with what we would have anticipated. And we were, to be honest, extremely relieved. This was subsequently done slightly less thoroughly for 100 different organisms that we held cryopreserved. And this first check actually had more failures in it than the subsequent, I've forgotten how many's on here, but say there's 30 or 40 on there. There was another 60 done. And that subsequent 60, all of them regrew. What you can see here are some red lines across, and some of those red lines are for samples where we hadn't had any recovery previously, and that's where I'm talking about the Euglena gracilis, or the example I have there. They're two, the same isolate in fact, and there was no regrowth on either sample, but we had previously tested those materials and there'd been no growth on them. They were separate batches, but historically on a card index they had viability, but we didn't ever get them to recover. That could be in part the recovery regime, quite probably. So we felt reassured by that, and then promptly didn't do anything for 6 years, as you do. You think, well, okay, it could have been worse. We may have damaged our samples, but at least we have the vast majority that were banked are still available. So more recently, under the N-Algae project, a EU-funded Interreg project, we've reinterrogated that data, and we've actually gone back and we're starting to look a bit more systematically. In context, these materials are no longer in that original cryobank. They've moved. So we're talking about materials that were previously stored in a different vessel. So they've had an additional sets of stresses insofar as almost all the old samples held in the CCAP cryostats have lived in a minimum of 3 or 4 different cryostats over the 40-year period, possibly more that I'm not aware of. So we looked at samples that had originally been stored in the top, middle, and bottom of different inventory stacks in the Jura which had the crisis. And this graph, I'm not sure it really should have error bars on it, but Kat was very keen to put error bars in everything. And it's percentage of cultures showing recovery, i.e. they grew back. That's it. So, and you can see that in the middle, actually, there's a magical increase, but these are not statistically significant data. In some cases, these are on relatively small numbers of examples, and they're not necessarily on the same isolates for this graph. But it looks like there's been no subsequent deterioration of the material, which is indeed what we would expect. What we had done prior to the cryo crisis, that we of course had material stored in 2 different Juras. So we had what I suppose in theory should be a master bank. In the reality of the CCAP structure, it's effectively a backup bank. It's where when we conventionally cryopreserve 15 new vials of any individual organism, 3 are taken out for a viability assessment, 2 go to a master bank where they should stay forever effectively, and the remaining 10 are in the working bank, and that's the system that we've had for years and years. So in this example, we have sacrificed one of our masters in order to look at differences between this one, pardon me, that's the next slide, is looking at a historic cryo after cryo storage. So I'll go to the next slide, which is maybe is too on. So this is, pardon me, this is back to looking at, I apologize, that was me off talking about 2 slides further on. This is looking at the 2 slides ago where we had before and after, and we've looked at individual organisms in this case. And you can see again, there are some where there is reduction and others where there is no reduction in viability. So we've, this is what I just discussed with you with looking at the backup versus the previously stored ones. And you can see that there's a differential recovery between samples in the thermally stable cryostat A, i.e. the backup cryostat, and the one that experienced the cryocrisis. And you can see for some organisms there's a very significant difference, although in the top picture there's actually a small amount of growth in one of those 2 flasks, and that subsequently recovered, but the other one, as far as we can tell, was dead. And this is what I was talking about before, where we're looking at working bank versus backup cryostat. And you can see that here, from these data, this is where we have only 1 replicate from the backup, but the working bank is a minimum of 2 vials that have been thawed. And there are examples here where we had no growth at all, and that is an artifact in part of the viability assay that we're doing. The pour plate method does not work for everything. It worked for some organisms, and it works for some organisms better than for others. But we're comparing as close as we can like with like, and you can see that there are at least a number of organisms here where the backup cryostat has numerically significantly higher levels of recovery than the working bank which suffered the cryocrisis. So how to move on from this to try to drill down and understand what's happening? I was hoping to have real data from this experiment, but unfortunately our first run, our first trial at this experiment hasn't worked satisfactorily insofar as the control data was not adequate to do a decent analysis. So we're currently redoing this, and these are the thermal traces from that original cryostat which boiled dry. We put nitrogen in it up to drawer 5, and we have probes in drawers 1, 6 and 12, and drawer 12 is the bottom one, and drawer 1 is the one at the very top. And you can see that as it boils dry, we were getting significant warming, and those spikes are there where we took the samples out to assay the viability. So this work is ongoing, and the results are coming soon, and I hope that before Christmas this work will evolve into a manuscript of some sort for submission to a journal. But to revisit conclusions or the sage wisdom accrued, well, the first thing I would say is don't let it happen. This was certainly the most stressful and tragic thing that I've had to do with regards to the cryoserved holdings of CCAP. Until we started getting that regrowth, I was in a very, very bad place and hugely worried. Clearly, one should follow all the best guidance and procedure that you should have samples in more than one cryostat, and my personal advice would be that you should have 2 working banks and a master, but this has cost implications for many small organizations. Ensure that there are multiple fail-safes in place to cover unexpected staff absences or people not following procedure. Don't panic. With luck, all is not lost. And perhaps the one thing that's come out of this that has been very encouraging is that temporary rewarming of stored samples resulted in, although it resulted in reduced levels of viability, for the vast majority of taxa that we hold, we have not lost those samples. Those samples still have validity, and even the ones where we may have lost viability, at least genetically, there is probably still material there that has scientific value. So just like to thank people who did a lot of the original cryo work, John, of course, Mark McClelland and Roland, as well as current and previous members of CCAP staff. Lots of the more recent work is done by research visitors and affiliated research students. So thank you very much.